These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So how would you read this expression aloud?
Okay. The definite integral of x cubed with respect to x from 0 to 1.
Very good. Excellent. That's a good way to read that. What's the graphical interpretation of this definite integral?
Okay. That is the area between the x-axis and the curve between 0 and 1.
Good. Which curve?
X cubed.
Yeah, x cubed curve. Okay, excellent. That was also very good. All right. How would we go about calculating this definite integral? According to the fundamental theorem of calculus, part 2, just to kind of outline in words, what's the general approach that we use for, we've just been practicing this, what's the general approach for calculating these definite integrals?
We take the antiderivative.
That's right. And then we evaluate the antiderivative at both limits of integration and subtract. Good. Now, again, we should pause for a second to think how amazing this is. Why on earth does an antiderivative calculate an area? Remember you were just telling me this is the area under the x cubed curve. Why on earth could you figure that out by finding a antiderivative? Well, we tried to give some indications in the earlier section for why that was somewhat reasonable. And the fact is, if you think about it long enough and meditate about it long enough and look at it from the right perspective, you can start to see why it does make good sense. But that's not really our main job in this course. Our main job is not to see why it makes sense. It's just to learn how to use it mechanically. So we're not going to go into more depth about why it works. But I do think it's worth thinking about the fact that at least initially it's kind of amazing that you can use antiderivatives to figure out areas. Okay. So again, we'll say, what does this symbol stand for?
That's a definite integral.
Yeah, and this means definite integral. Okay, now changing the subject slightly. Well, actually, changing the subject slightly. How would you read this aloud?
That is the derivative of 1/4 x to the 4th.
Good. And great. And what is that derivative?
That is, let's see.
You can work it out on paper if you like.
Okay. Well, it's just going to be, yeah, let me work it out on paper. So 4 times 1/4, which is just 1. So then x cubed. X cubed.
Good. Good. So how would you read this equation aloud?
The derivative of 1/4 x to the 4th is x cubed. And then we can also say that the antiderivative of x cubed is 1/4 x to the 4th.
Good. Excellent. Okay, now notice, do we have any notations for indicating derivatives? Yes. One of the notations we have for derivative is prime. By the way, remember we have another notation as well. We could also write that like this. If you recall, we actually have two different notations for derivatives. Two notations for derivatives. I don't know if you noticed or thought about this, but so far, we've never had a notation for antiderivative. We've been talking about antiderivative, we've used the word antiderivative, but we've never actually invented a notation for antiderivative the way the prime means derivative. Well, now it's finally time to to satisfy that burning need that we have for a notation for antiderivative. We're finally ready to do that. So what would be a good notation for antiderivative? Well, here's the way the mathematicians thought about it. Remember, here we have a definite integral. But what's the basic operation that you use for calculating definite integrals? How do you...
We take the difference of the antiderivatives at
good.
certain...
Excellent. Good. Great. Excellent. More than great. So the point is you use antiderivatives. So they decided to use this symbol for an antiderivative. So this is the symbol for taking an antiderivative. This is the symbol for taking an antiderivative. But wait, isn't that the same symbol we used here? Well, no, the mathematicians would say. You're not looking carefully enough. This is the symbol when we don't put in numbers.
Okay.
All right. So I don't know whether this was a good idea or a bad idea, but this is the way they decided to do it. So the point here is that when you use, so this is what's called an integral sign, right? But the mathematicians have said an integral sign with numbers is a completely different thing from an integral sign without numbers. So we just have to accept that. That's the decision they made. An integral sign with numbers means something completely different from an integral sign without numbers. What does an integral sign with numbers mean? An integral sign with numbers means definite integral, which we know means area. What does an integral sign without numbers mean? An integral sign without numbers means antiderivative. So it's just a definition. The mathematicians are in charge. They can define things however they want. So these are the definitions that they used. All right, so we just have to learn those two definitions. So now finally we have a symbol for taking the antiderivative. So what does an integral sign with numbers mean?
The definite integral.
Yeah. And what does an integral sign without numbers mean?
The antiderivative.
Yeah, actually, I shouldn't say numbers, because these don't have to be numbers. They could be letters. What I should be saying is that if you have an integral sign with limits of integration, then that means a definite integral. And if you have an integral sign with no limits of integration, that means the antiderivative. Okay, so that's just a new definition here. Okay, so this here is what's called the antiderivative. Now, what were they thinking? Didn't they realize this could be confusing to use two symbols that look so similar to mean different things? Well, maybe they noticed that, but the reason they decided to do that, the reason why this seems like a good idea to them, is because they wanted to show how closely related taking antiderivatives is to definite integrals. So that's what they were thinking. I don't know if that was a good thought, but they were thinking. Basically, remember, they were really excited. The mathematicians were really excited with this tremendous discovery that the way to find definite integrals is by taking antiderivatives. So they really want to hammer home how clever they were to figure that out by using this symbol to show how closely related antiderivatives are to definite integrals. So that's the point. We're using two symbols that look very similar to emphasize the fact that taking antiderivatives is very, very closely related to finding definite integrals. Okay. All right. By the way, notice when you use this notation, you still always have to put this dx on the end. So this means taking the antiderivative of x cubed with respect to x. This is the antiderivative of x cubed with respect to x. The dx is kind of just like a closing parenthesis. It says, hi, this is the end of the antiderivative. Okay, so that's what that means. Okay, so what does this mean?
This is the antiderivative of cosine of x with respect to x, which is sine of x.
That's right. You went the extra mile and actually figured it out. Good. So this is the antiderivative of cosine x. Excellent. And as you said, that would be equal to this. Not quite. It would be this.
We expect. Oh, true.
So we got to go back to remembering that. Remember, when we do definite integrals, do we need to worry about the c?
We don't.
But when we do general antiderivatives, we do need the c. And that's certainly something we can lose credit for. So we still have to keep watching out for that. Okay, good. What does this mean?
This This is the definite integral of cosine of x with respect to x between 0 and pi.
Okay, good. Excellent. What's the graphical interpretation of this?
This is the area that's between the x-axis and the curve cosine of x.
Good, between 0 and pi. Excellent. It's a little hard to define because technically it's the area between the cosine x curve and the x-axis between 0 and pi. If you remember to count areas above the x-axis is positive and areas below the x-axis is negative. So giving a full interpretation would be more than we can expect. But I think we are familiar with that in our head. So we can just say this represents the area between the curve and the x-axis between 0 and pi. Okay, good. So we don't want to confuse these two notations. They mean two different things. Notice this does not directly mean an area. This is not directly an area. It's an antiderivative, although we do know that we can use antiderivatives to find areas. Okay. Okay, good. Now, the mathematicians, at the same time that they were inventing this symbol, they also invented another name for antiderivatives. They have another name for antiderivatives. I don't know if you picked up on this from class. What's another name for this symbol? What's another name for this antiderivative symbol?
Let's see. Yeah, I'm blanking.
That's okay. They decided to call it the indefinite integral.
Okay. Yep, sounds familiar.
Okay. So would you agree indefinite integral is a synonym for antiderivative?
Yeah.
Yeah, they mean the same exact thing. So maybe this is unfortunate. Why couldn't they just stick to just one term? I don't know. But they invented two terms for the same exact thing. Why did they do that? Again, it's because they were so excited about the connection between antiderivatives and definite integrals that they really wanted to hammer that home by giving them more similar names. They said, well, antiderivative doesn't really show how useful this is for finding definite integrals. Let's call it the indefinite integral to really show how terrific it is that we figured out that we can use antiderivatives to find definite integrals. Okay. Do you see why they might call this indefinite? It's indefinite because there's no definite limits of integration here. Perhaps that's what they meant. So the definite integral is the one with limits of integration, and the indefinite integral is the one with no limits of integration. So how would you read this aloud? Now we have two ways to read this aloud. We could say this means the antiderivative of cosine x. Or you could say this means the indefinite integral of cosine x. Those are both perfectly fine ways to read it. They both mean the same exact thing. And how would you read this aloud? The definite integral. All right, so indefinite integral means the same thing as antiderivative. They're both different from the definite integral.
Okay.
Okay, so here's a problem. Maybe we'll keep trying to do this on my screen. So you can try this on paper if you want, and then tell me your answer, or talk me through what your work is. So when you're ready, talk me through your steps and tell me what your answer is.
Okay, so this is the antiderivative of 8 with respect to x, and that is 8x plus c.
Like so?
Yep.
Okay, excellent. And you remembered the plus c. Excellent. What does the c stand for?
A constant.
Right, so 8x plus a constant. Okay, perfect, great. That's exactly right. So how would you read this equation aloud?
The antiderivative of 8 with respect to x is 8x plus c, or you could say the indefinite integral of 8 with respect to x is 8x plus c.
Perfect. Those are both exactly right. Okay, excellent. All right, let's try this problem.
Okay. The antiderivative of pi with respect to theta is, let's see, that would be pi x plus c.
Okay, like this?
Yep.
Now you read that correctly. You read it very carefully, but you didn't quite pay attention to part of what you read.
Pi theta.
That's right. This is something that we have to watch out for here. It's easy to kind of ignore this piece, but this piece is not meaningless. This is important because it tells us what variable we're using. All right, so what's the answer?
Pi theta plus c.
There you go. Okay. So then we'd have this answer. Good. And now how would you read this aloud?
The indefinite integral of pi with respect to theta is pi theta plus c.
Great. By the way, what rule are you using here? On these last two problems, you've been using the constant rule for anti-differentiation. The constant rule for anti-differentiation. Or I guess now we could also call it the constant rule for taking an indefinite integral. Okay. One thing that you did that was good here is you didn't say this was the answer. I think a lot of people would be tempted to think that this is the answer. They would try to use the power rule. How do we know the power rule doesn't apply here? Because the power rule only applies, remember, when the base is a variable. But is this a variable?
No, it's not.
It's a constant. Okay. Well, you didn't make that mistake, but just to warn you, that continue, please, not to make that mistake. All right, good. The point is, it kind of looks like a variable. It looks more like a variable than 8 does, so we have to remember it's really a constant. All right. Okay, let's solve this problem.
Okay. The antiderivative of -3 with respect to t. Okay, so that's going to be -3t plus c.
Okay, that's exactly right. Let's try this one.
So, 1?
Yes.
Okay. The antiderivative of 1 with respect to x is x plus c.
Okay. Okay, so very good. So now we need to start making a master list of our techniques for integration. So we'll start a table here. So we'll have a table of indefinite integrals. What do you think this symbol stands for?
Constant.
Yeah. So what should I write here?
Let's see. K x plus c.
Good. We have to include the plus c here because I wrote this as an indefinite integral. An indefinite integral always means that you include the plus c. Okay, so this is the constant rule for integration. I think we got that down, so I'll go back down to here. Okay, try this problem. You can try working this out on paper and tell me what you get.
Okay. Alright, so we're taking the antiderivative of 3x to the 4th with respect to x. So we add 1. So this is going to be 3/5 x to the 5th plus c.
Okay, great. And how would you read this aloud?
The antiderivative of 3x to the 4th with respect to x is 3/5 x to the 5th plus c.
Great. And what was the other way to read it aloud?
The indefinite integral of 3x to the 4th with respect to x is 3/5 x to the fifth plus c.
Okay, excellent. Very good. So what does indefinite integral mean?
The antiderivative.
Yeah, they're just two different terms for the same thing. Very good. Let's answer this.
Okay. The antiderivative of x with respect to x is 1/2 x squared plus c.
How would you check that?
We can take the derivative of 1/2 x squared plus c, and we should get x. And when we do that, we get 2 times 1/2, which is 1, and 2 minus 1, so we get x.
Good, because what's the derivative of the c?
0.
Because of the constant rule. Okay. Okay, well, I think we're ready to add that to our list as well. So another type of integral is this. What does the n stand for here?
The n stands for some number.
Constant or a variable?
Constant.
Yeah. The x must be a variable because it matches the dx. dx has to refer to a variable. Okay, so how would we summarize this? What's this answer?
Okay, so this is x to n plus 1 over n plus 1 and then plus c.
Excellent. I personally find it more convenient to write that like this, but your answer was correct. I think in the long run this tends to be easier because it makes it easier to make simplifications, but they're both the same thing. So this is the power rule for integration. We've already talked about this. This is our power rule for integration. Good. Okay, talk me through how you would solve this.
Okay, the antiderivative of 1 over x cubed with respect to x. So we bring x cubed to the top, and we can rewrite this as the antiderivative of x to the negative 3 with respect to x. Now we can take the antiderivative, and that is going to be, let's see, you divide by negative 2, which means, okay, so it would be negative 1/2, negative 1/2 x to the negative 2 plus c, and I just need to double check this real quick.
Sounds good.
So negative 2 times negative 1/2, so x, and then yeah, that's right.
Okay, excellent. So that sounded like an excellent process. One thing you did there that was particularly excellent was it sounded like you were using good notation. So here, this first step, you hadn't taken the antiderivative yet. You were just rewriting the function. So the thing that you did that was especially good is that you specifically said we have to still keep, it sounded like you were saying we have to keep the integral sign. So that was good. We have to keep the integral sign here because we haven't yet taken the antiderivative, and here we drop it out. By the way, this is one thing, this is a notation we never had up till now. Up till now, we never really had a very good notation for indicating when we had taken the antiderivative and when we hadn't, because we hadn't invented a symbol for antiderivative yet. So now this will be an improvement to our notation because now we can actually show when we've taken the antiderivative and when we haven't, and you did that correctly. So this was just another application of that power rule. You rewrote this so you could apply the power rule. Excellent. Okay, so let's try this one.
Okay, so this is the antiderivative of x to the negative 1 with respect to x, so we can rewrite this as the antiderivative of 1 over x with respect to x. And then now we can take the antiderivative, and that is the natural log of the absolute value of x plus c.
Okay, perfect. Excellent. I was trying to trick you or trap you into applying the power rule here by leaving it on the screen, but you didn't fall for it, so that's good. So I think we've discussed in the past that the power rule doesn't work in this case. If you try to apply the power rule here, you end up dividing by 0. So you didn't fall for the trap. That's good. Okay, so it looks like we're remembering that, so we can add that to our list. Now, I would actually, one thing you did that is maybe not necessary. Maybe we can just remember it like this. So what does this come out to be?
The natural log of the absolute value of x plus c.
Good. So my point is, maybe there's no need to rewrite this as 1 over x. If we just have memorized that the antiderivative of x to the negative 1 is natural log of x, you can go straight to here. I'm not saying there's anything wrong with it. There's nothing wrong with how you did it. But it might be good just to be able to recognize that both of these mean the same thing, and they mean this. So like I said, the way you did it was exactly correct, but we can summarize it this way to show that these both mean the same thing. So this is the case where the power rule doesn't work, doesn't apply, and you remembered that. That's good. Okay, what's this?
Okay, the antiderivative of sine of x with respect to x. So what gives us sine of x? Derivative of cosine, negative sine of x. So the antiderivative of sine of x with respect to x is negative cosine of x plus c.
Excellent.
Okay, this is the antiderivative of cosine of x with respect to x. So what gives us cosine of x? That would be sine of x. So the answer is sine of x plus c.
Okay, that's very good as well. One moment. Okay, now there's 2 more types of antiderivatives that you and I have talked about. 2 more that should go in this table. And then there's more we'll have to get into next. So there's a bunch more stuff we haven't talked about yet, but there's 2 more we have talked about that we should include in the table. Can you remember what's one other type of antiderivative that we've learned how to do? Besides the ones we have written down here.
The antiderivative of, what's the term? Natural, no. Exponential functions.
Oh,
something like that.
So what should I write here?
E to the x.
Okay, you know, I wasn't thinking of that, but I should have been. I forgot about that one. Excellent. Okay, yeah, I wasn't thinking of that, but I should have been. I totally forgot about that, so you're right. We should include that. So yeah, these are what are called natural exponential functions.
Natural exponential functions.
That's right. This would just be an ordinary exponential function. But when you got the base e, it's called the natural exponential function. Okay, well, what would this be?
E to the x plus c.
There you go. Okay, that's good that you recalled that. Very good. Okay, now I think there's 2 more. 2 more that we've talked about together. Can you remember one more expression that we've learned how to take the antiderivative of, a different type of rule than the ones we have written down here?
So we did power function, we did natural logs, we did trig, I did trigs, functions, and let's see. Oh, okay, yeah, we did the antiderivatives of one over 1 plus x squared with respect to x, and that is inverse of tangent x plus c.
Very good, very good. That's right. Now, when you take the test, you're not going to get to bring any notes, right?
Right.
And the instructor's not going to give you a formula sheet, are they?
No.
Okay, so we really have to work on memorizing these, because what we're going to be doing next is harder antiderivatives, much harder. The antiderivatives we're going to go to next are going to be much harder, but the way to solve them is by relying kind of on these tools. So we need to be able to quickly come up with these tools out of our heads. in order to be able to solve those. So it's not good enough to be able to get these right if someone prompts you with them. You have to be able to think of these on your own in order to apply them to problems. That's why I asked you that question, and you did a good job of thinking about it until you came up with it. So that's good. That's good that you remembered this. This is something else that, so we need to be able to just run through these in our head, because what you're going to do is you're going to be seeing harder antiderivatives, and you just have to say to yourself, well, can I simplify using this constant rule? Can I simplify this using the power rule? Can I simplify this by looking for x minus 1 to the negative 1? Can I simplify this by looking for trig functions? Can I simplify this by looking for natural exponential functions? And if none of those work, hopefully you'll say, well, gee, another trick I have is maybe there's a 1 over 1 plus x squared somewhere in there. But the only way you would ever even look for the 1 over 1 plus x squared is if you could kind of think of it without being prompted. And you did. Okay, so that's good.
Okay.
All right, and then now there's one more.
Right. We're going to focus on, I believe, sine. So the antiderivative of 1 over the square root of 1 minus x squared. I believe it is, yeah. And that is, sorry, sine, the inverse of sine x plus c.
Good. Inverse sine of x plus c. Okay. All right. Now I think those are the ones that we've gone over so far. Okay. So I was going to say that you need to have this memorized, but I think you're pretty much there. You pretty much do have it memorized. You have to have it kind of super memorized, like I was saying, so that you can come up with these on your own. And you're not too far from that either. I think you're already pretty comfortable with these. So what we have left is there's a few more of these rules that you and I haven't talked about before that we need to add to the table. But then we have to kind of learn harder antiderivative problems where you have to do kind of more work, basically, to apply it. That's kind of what the last two sections are about, harder and harder antiderivatives. The key to those, though, is having complete mastery over the ones we've already gone over. Like I said, right now I feel like you're pretty solid on this. I think you're pretty solid on the information we've already gone over. So that should stand us in good stead going forward with this section.